High above the clouds, in one of the driest and darkest places on Earth, humanity is building a machine that will redefine our understanding of existence. On a remote mountaintop in the Atacama desert of northern Chile, where the air is so clear it feels almost unreal and the sky burns with more stars than most people have ever imagined, a colossal structure is rising from rock and silence. This is not just another observatory. This is not simply an upgrade to what we already have. This is the Giant Magellan Telescope, a machine so ambitious, so powerful, and so technologically advanced that it is designed to surpass even the revolutionary James Webb Space Telescope in certain critical ways. And when it opens its enormous eye to the cosmos, the universe as we know it may never look the same again. For decades, space telescopes have captured the imagination of the world. The Hubble Space Telescope gave humanity breathtaking images, pillars of gas-forming stars, galaxies colliding in silent chaos, and distant light traveling billions of years to reach our eyes. Then came JWST, unfolding like a golden mechanical flower in deep space, positioned at the gravitational balance point known as L2, peering deeper into cosmic history than ever before. It shocked the world with razor-sharp infrared images of ancient galaxies that seemed to appear far earlier than our theories predicted. But even as JWST continues to transform astrophysics, scientists and engineers have been quietly preparing something even more formidable, not floating in space, but anchored firmly to Earth. The Giant Magellan Telescope, often simply called GMT, is not a single mirror like traditional telescopes. It is a masterpiece of engineering composed of 7 massive primary mirrors, each one 8.4 meters in diameter. When combined, they create a single optical surface equivalent to a 24.5-meter telescope, an enormous light-collecting giant capable of gathering more than 4 times the light of JWST and nearly 10 times the resolution of the Hubble Space Telescope in certain wavelengths. Imagine a telescope so powerful that if it were capable of spotting a candle flame on the moon, it would see it flickering. That is the scale of precision we are talking about. That is the level of detail humanity is about to unlock. But power alone is not what makes GMT extraordinary. It is where it stands and how it works. Unlike JWST, which observes primarily in infrared from the vacuum of space, GMT will operate from the ground, yet it will overcome Earth's atmospheric distortion using one of the most advanced adaptive optics systems ever designed. Thousands of times per second, its mirrors will subtly reshape themselves, correcting for turbulence in the atmosphere in real time. The result? Images so sharp they will rival, and in some visible wavelengths surpass, those taken from orbit. It is as if Earth itself is learning how to remove the blur from its own vision. The site chosen for this colossal observatory is no accident. The Las Campanas Observatory, perched high in the Andes Mountains, offers some of the clearest skies on the planet. The region experiences minimal rainfall, almost no light pollution, and stable atmospheric conditions that astronomers dream of. For generations, scientists have traveled to this part of Chile to glimpse the universe with unparalleled clarity. Now, with GMT, that clarity will reach an entirely new level. The mountain itself is being reshaped to support a rotating dome large enough to house one of the most advanced optical systems ever conceived. Why build such a machine now? Because we are living in a golden age of astronomical discovery, and also in an age of profound cosmic mystery. We know that ordinary matter, the atoms that make up stars, planets, and people, accounts for less than 5% of the universe. The rest is dark matter and dark energy, invisible forces shaping cosmic expansion and galactic formation. JWST has begun to challenge our understanding of early galaxy formation, revealing massive structures that seem to have formed astonishingly quickly after the Big Bang. But to truly understand whether our cosmological models are incomplete, scientists need more data, sharper images, and deeper spectroscopy. That is where GMT enters the story. GMT will not simply take pictures. It will analyze light with extraordinary precision, splitting it into spectra that reveal chemical compositions, temperatures, velocities, and distances. It will search for biosignatures in the atmospheres of exoplanets orbiting distant stars. Imagine detecting oxygen, methane, or water vapor in the thin atmospheric layer of a rocky world dozens of light years away. Such a discovery would not merely suggest life might exist elsewhere, it would fundamentally alter humanity's place in the universe. The possibility is no longer science fiction. It is a real scientific objective. Consider the search for Earth-like planets. Over the last few decades, missions like Kepler Space Telescope and Transiting Exoplanets Survey Satellite have identified thousands of exoplanet candidates. We now know that planets are common throughout the Milky Way, but discovering them is only the first step. To truly understand them, to probe their atmospheres and look for chemical fingerprints of life, we need telescopes with enormous light-gathering capability and extreme resolution. GMT's massive mirror array will make it one of the most powerful tools ever built for this purpose. In some ways, comparing GMT and JWST is like comparing a deep-sea submarine to a powerful mountaintop observatory. JWST sees the universe in infrared from beyond Earth's interference, optimized for observing the earliest galaxies and star-forming regions obscured by dust. GMT, by contrast, will excel in visible and near-infrared wavelengths with extraordinary resolution, particularly for detailed follow-up observations. Together, they form a complementary system, space and Earth working as partners. But in specific areas, such as resolving fine details of distant objects or studying stellar motions in nearby galaxies, GMT's enormous mirror will give it an advantage. The engineering challenges behind GMT are almost as breathtaking as the science. Each of its 7 mirrors is cast in a rotating furnace at the University of Arizona's Mirror Lab, where molten glass spins in a giant mold, forming a honeycomb structure that is both lightweight and incredibly rigid. After cooling for months, each mirror is polished with nanometer precision, smooth to within fractions of the wavelength of light itself. The level of perfection required is nearly unimaginable. A surface error smaller than a human hair could distort astronomical data collected from billions of light years away. And yet, despite the complexity, despite the cost, projected in the billions of dollars, and despite the technical risks, international partners have committed to making this vision real. Universities and research institutions across the United States, Australia, Brazil, South Korea, and Chile are collaborating on this monumental effort. It is a reminder that exploration, at its best, transcends borders. The universe belongs to no one nation. It belongs to everyone. When GMT begins full operations later this decade, it will peer into the hearts of galaxies, measure the motions of stars around supermassive black holes, and perhaps refine our understanding of gravity itself. It will test Einstein's theory of general relativity in extreme environments near event horizons. It will map the distribution of dark matter by observing gravitational lensing with exquisite clarity. It may even detect the faint glimmer of the very first generation of stars, the so-called population 3 stars, whose existence has long been theorized but never directly observed. And perhaps most profoundly, it will remind humanity that our curiosity is limitless. We build these giant eyes not because we must, but because we cannot help ourselves. Since the first humans looked up at the night sky and wondered about the moving lights above, there has been an unbroken chain of curiosity stretching across millennia. GMT is simply the latest, and perhaps one of the boldest, expressions of that desire to know. This telescope represents more than technological ambition. It represents hope. Hope that we can answer some of the deepest questions ever asked. How did the first galaxies form? Are we alone? What is the true fate of the universe? With every mirror polished and every instrument calibrated, we move closer to answers that once seemed forever beyond reach. Its true power does not come only from the size of its mirrors, but from the technology that allows it to bend Earth's atmosphere to its will and extract cosmic secrets hidden in the faintest traces of light. To understand why GMT is so extraordinary, we must first understand the problem that has haunted ground-based astronomy for centuries: Earth's atmosphere. The same blanket of air that makes life possible distorts starlight as it travels downward. When light from distant galaxies enters our atmosphere, it passes through turbulent layers of air with constantly shifting temperatures and densities. This turbulence bends the light unpredictably, making stars appear to twinkle and blurring images captured by telescopes. For decades, space telescopes like the Hubble Space Telescope and later the James Webb Space Telescope escaped this distortion by operating beyond Earth's atmosphere. But GMT is taking a different approach. Instead of escaping the atmosphere, it is mastering it. At the core of this mastery lies one of the most advanced adaptive optics systems ever conceived. Adaptive optics is a technology that measures atmospheric distortion in real time and corrects for it by subtly reshaping a telescope's mirrors. In GMT's case, this correction happens thousands of times per second. Think about that. Every second, the system analyzes incoming light from a reference star, either a natural star or an artificial one created by a powerful laser beam projected into the sky, and calculates exactly how the atmosphere is warping that light. Then, using actuators positioned behind thin deformable mirrors, it adjusts the mirror's surface by microscopic amounts. These adjustments are so precise that they are measured in nanometers, billionths of a meter. The result is breathtaking. Instead of blurry, distorted images, GMT will achieve clarity approaching the theoretical limit of its enormous aperture. In visible wavelengths, this means resolution sharper than what JWST can achieve in infrared. In practical terms, it means being able to resolve structures within distant galaxies that were previously smudges of light. It means separating tightly packed stars in crowded stellar clusters. It means measuring the subtle wobble of stars caused by orbiting exoplanets with unprecedented precision. And then there are the mirrors themselves, perhaps the most iconic feature of GMT. Unlike traditional telescopes with a single monolithic mirror, GMT consists of 7 massive primary mirrors arranged in a flower-like configuration. Each mirror is 8.4 meters in diameter, cast at the University of Arizona's Richard F. Karras Mirror Lab using a process that spins molten glass in a rotating furnace. This spinning creates a honeycomb internal structure, making each mirror lighter and more stable without sacrificing strength. But casting is only the beginning. After months of cooling, each mirror undergoes years of polishing, achieving a surface smoothness so precise that its imperfections are smaller than a fraction of the wavelength of light. To put it in perspective, if the mirror were the size of the United States, the largest bump would be only a few inches tall. When these 7 mirrors act together, they create a single effective aperture equivalent to 24.5 meters. That means GMT will collect more than 4 times as much light as JWST and over 6 times more than the largest single-mirror telescopes currently operating. More light means fainter objects become visible. More light means faster observations. More light means deeper understanding. But GMT's real advantage lies not just in raw light collection, but in spectroscopy, the science of breaking light apart into its component colors to reveal physical information. Every element leaves a unique fingerprint in the light it emits or absorbs. By analyzing these spectral fingerprints, astronomers can determine the chemical composition of stars, galaxies, and planetary atmospheres. GMT's spectrographs will be among the most powerful ever built, capable of detecting minute shifts in wavelength caused by motion, gravity, or chemical processes. Consider what this means for exoplanet research. Missions like Kepler's Space Telescope and Transiting Exoplanets Survey Satellite have identified thousands of candidate worlds orbiting distant stars. JWST has begun analyzing the atmospheres of some of these planets, detecting water vapor, carbon dioxide, and even hints of complex chemistry. But many of these observations are limited by time and sensitivity. GMT will complement JWST by conducting high-resolution follow-up studies, searching for biosignatures such as oxygen, methane, and ozone, gases that, on Earth, are strongly linked to biological activity. Imagine pointing GMT toward a rocky planet orbiting within the habitable zone of a nearby red dwarf star. As the planet passes in front of its star, a small fraction of starlight filters through the planet's atmosphere. That light carries subtle imprints of atmospheric chemistry. GMT's enormous collecting area and high-resolution spectrographs could detect these imprints with extraordinary precision. If a combination of gases appears that cannot be explained by geology alone, it would suggest something far more profound, the possibility of life. But the revolution does not stop with exoplanets. GMT will also probe the earliest epochs of cosmic history. JWST has already revealed surprisingly mature galaxies existing just a few 100 million years after the Big Bang. These discoveries challenge established models of galaxy formation. How did such massive structures form so quickly? Were the first stars more massive than predicted? Did black holes grow at unprecedented rates? GMT will tackle these questions by providing ultra-high-resolution spectroscopy of distant galaxies, measuring their masses, star formation rates, and chemical enrichment with unparalleled detail. And then there are black holes, the gravitational titans lurking at the centers of galaxies. Nearly every large galaxy, including our own Milky Way, hosts a supermassive black hole at its core. By tracking the motions of stars orbiting close to these invisible giants, GMT will measure black hole masses with extraordinary precision. It may even test aspects of Einstein's general theory of relativity under extreme gravitational conditions. In doing so, it could refine our understanding of spacetime itself. The synergy between GMT and JWST will be one of the defining features of modern astronomy. JWST, positioned at the Sun-Earth L2 nearly 1.5 million kilometers from Earth, excels at observing faint infrared signals from the early universe in dust-shrouded star-forming regions. GMT, anchored on Earth but empowered by adaptive optics, will zoom in with astonishing detail. Where JWST identifies intriguing targets, GMT will dissect them. Where JWST reveals ancient galaxies, GMT will analyze their internal structure. Together, they form a two-pronged attack on cosmic ignorance. Construction of GMT is itself a testament to global collaboration. Institutions from the United States, Australia, Brazil, South Korea, and Chile contribute funding, engineering expertise, and scientific leadership. Massive steel structures are being assembled. The rotating dome is being constructed to withstand fierce mountain winds. Precision instruments are being designed in laboratories across continents. Every bolt, every cable, every line of code is part of a coordinated effort to build one of humanity's most ambitious scientific instruments. There is something poetic about building such a colossal machine in the silence of the Andes. While cities below glow with artificial light, the mountain remains dark, intentionally so, protected by regulations that limit light pollution. The night sky above Las Campanas is not merely dark, it is profoundly dark. It is the kind of darkness that reveals the Milky Way as a luminous river stretching from horizon to horizon. It is the kind of darkness that makes you feel small, and yet connected to something vast beyond comprehension. GMT is scheduled to begin scientific operations later this decade, and when it does, the data will begin to flow. Petabytes of information, spectra from distant worlds, images sharper than any ground-based telescope has ever produced, observations that may confirm, challenge, or overturn decades of theoretical work. And perhaps that is the most exciting part of all. The history of astronomy teaches us that whenever we build a more powerful telescope, the universe surprises us. When Galileo first pointed his small refractor toward Jupiter, he discovered moons orbiting another world. When Hubble launched, it revealed that the universe was expanding at an accelerating rate. When JWST opened its golden mirror, it showed galaxies forming earlier than expected. GMT will almost certainly deliver surprises of its own, phenomena we have not yet imagined, questions we have not yet asked. Because in the end, the Giant Magellan Telescope is not merely a bigger eye. It is a sharper mind, a tool designed to push the boundaries of human knowledge, a bridge between theory and observation, a machine built not just to see farther, but to understand deeper. On a silent night in the high mountains of the Atacama Desert, when the wind moves gently across the rocky ridges and the Milky Way stretches across the sky like a glowing river of ancient light, the dome of the Giant Magellan Telescope will slowly rotate into position. Massive steel panels will slide open. The 7 enormous mirrors will align with nanometer precision. Adaptive optics systems will awaken. Lasers will fire into the sky, creating artificial stars. And in that moment, humanity's newest and most powerful eye will open. This is not just the activation of a telescope. It is the activation of possibility. In parts 1 and 2, we explored GMT's colossal structure and revolutionary adaptive optics, how it will gather more light than nearly any optical telescope ever built and achieve resolution sharp enough to redefine what ground-based astronomy can do. But now we must confront the ultimate question: what will it discover? What truths lie waiting in the darkness? Because history teaches us something profound. Every time humanity builds a more powerful telescope, the universe refuses to behave exactly as we expect. When the Hubble Space Telescope launched, it revealed that galaxies were not just drifting apart, they were accelerating away from each other, driven by a mysterious force we now call dark energy. When the James Webb Space Telescope began sending back images, astronomers were stunned to see massive, mature galaxies forming shockingly early in cosmic history. These discoveries were not incremental. They were disruptive. They forced scientists to revise theories, rewrite textbooks, and rethink assumptions about how the universe evolves. GMT stands poised to deliver the next disruption. One of its most ambitious goals is to explore the earliest chapters of cosmic history, the era when the first stars ignited. These primordial stars, known as population 3 stars, were forged from pure hydrogen and helium left over from the Big Bang. They contained none of the heavier elements that now form planets and life. They were likely enormous, short-lived, and violently explosive. And yet, despite decades of searching, none have been directly observed. With its extraordinary light-gathering power and high-resolution spectroscopy, GMT may finally detect the chemical fingerprints left by these ancient titans. By studying the faint light of extremely distant galaxies, light that has traveled for more than 13 billion years, astronomers could uncover evidence of these first stars. That would mean we are witnessing the universe's infancy, seeing the moment when darkness first gave way to light. But perhaps even more transformative is GMT's role in the search for life beyond Earth. For centuries, humans have asked the same question: are we alone? It is a question that transcends science. It touches philosophy, religion, and identity. It defines how we see ourselves in the vastness of space. In recent decades, missions like Kepler Space Telescope and transiting Exoplanets survey satellite have revealed that planets are not rare, they are everywhere. Nearly every star in the sky likely hosts at least one planet. Some of these planets orbit within the habitable zone, where temperatures allow liquid water to exist. But finding a planet is only the beginning. Understanding its atmosphere, its chemistry, is where the real story begins. GMT will analyze the atmospheres of rocky exoplanets orbiting nearby stars with unprecedented precision. When a planet passes in front of its star, a tiny fraction of starlight filters through its atmosphere. That light carries chemical signatures: oxygen, methane, carbon dioxide, water vapor. Individually, these molecules might not mean much. But together, in certain combinations, they can signal biological processes. On Earth, oxygen and methane coexist because life constantly replenishes them. Without life, they would react and disappear. If GMT detects a similar imbalance on another world, it would be one of the strongest indicators that life exists elsewhere. Imagine the announcement. Imagine the data appearing on screens in observatories around the world. Imagine the careful verification, the skepticism, the repeated measurements. And then imagine the confirmation. A distant planet, dozens of light years away, showing chemical signs that cannot be explained by geology alone. The discovery would not mean alien civilizations. It might mean microbial life, simple organisms floating in oceans beneath alien skies. But even that would be enough. It would mean that life is not unique to Earth. It would mean biology is not an accident, but perhaps a cosmic tendency. And the psychological impact would be enormous. Humanity has undergone worldview shifts before. We learned that Earth is not the center of the universe. We learned that our galaxy is only one among billions. We learned that our sun is an ordinary star. Each revelation made us feel smaller, yet somehow more connected. The discovery of extraterrestrial life would be another such shift. It would unite science and wonder in a way few events ever have. Beyond life, GMT will explore black holes with extraordinary detail. At the centers of galaxies lie supermassive black holes millions or billions of times the mass of our sun. By tracking the motion of stars orbiting close to these gravitational monsters, GMT will measure their mass and test the limits of Einstein's theory of general relativity. Subtle deviations from predicted motion could hint at new physics, perhaps clues toward a deeper understanding of gravity itself. And then there is dark matter, the invisible scaffolding holding galaxies together. Though it cannot be seen directly, its presence is inferred through gravitational effects. GMT's sharp resolution will map how galaxies distort the light of objects behind them, a phenomenon known as gravitational lensing. By measuring this distortion precisely, astronomers can map the distribution of dark matter with unprecedented clarity. This may bring us closer to identifying what dark matter actually is: a particle. A new force, something we have not yet imagined. The synergy between GMT and JWST will define a new era of astronomy. JWST, orbiting at the Sun-Earth L2 nearly 1.5 million kilometers away, observes the cosmos primarily in infrared, peering through cosmic dust and into the earliest epochs. GMT, anchored firmly on Earth yet empowered by adaptive optics, will provide sharper detail in visible and near-infrared wavelengths. Where JWST discovers, GMT will analyze. Where JWST reveals ancient galaxies, GMT will dissect their structure and dynamics. Together, they form a partnership across space and Earth, a coordinated exploration of the cosmos. But perhaps the most important impact of GMT is not scientific. It is inspirational. In an age often dominated by conflict, division, and short-term thinking, projects like the Giant Magellan Telescope remind us that humanity can still dream long-term. It is an international collaboration involving institutions from the United States, Australia, Brazil, South Korea, and Chile. It requires patience, precision, and trust. It is built not for immediate profit, but for knowledge. And knowledge is powerful. When a child looks at an image captured by GMT, a distant galaxy in stunning clarity, a newborn star wrapped in glowing gas, a spectrum revealing the chemistry of an alien atmosphere, that image may inspire the next generation of scientists, engineers, and thinkers. The telescope does not just look outward. It pulls humanity forward, because ultimately, the Giant Magellan Telescope is not only about seeing farther than ever before. It is about understanding who we are in the vast cosmic story. From the first humans who stared at the stars without knowing what they were, to Galileo lifting a small lens toward Jupiter, to the launch of Hubble, to the unfolding of JWST's golden mirrors, there has been a continuous thread of curiosity stretching across time. GMT is the next chapter in that story. And when its 7 mirrors gather ancient light, light that left distant galaxies before Earth even formed, that light will travel through adaptive optics, into spectrographs, into data systems, into human minds. We will analyze it, question it, argue over it, celebrate it, and somewhere within that light may lie answers to questions humanity has asked for thousands of years. How did it all begin? What is the universe made of? Are we alone? The Giant Magellan Telescope is not just more powerful than JWST in certain ways. It represents a new stage in our cosmic journey, a stage where Earth itself becomes a platform for precision equal to space, where technology bends the atmosphere into clarity, and where the next great discovery could arrive at any moment. The dome will open, the mirrors will align, the universe will speak.